So my name's Jordan. I'm going to talk a bit about my honours project, which was to find the best proof of a statement called Kurzweil's lemma. So first, let's talk about what does it mean for a proof to be the best? So there are many ways you can measure this, right? There's sort of one objective way to measure it would be the best proof is the one that uses the least assumptions. Okay, so if you prove something with less assumptions, it's a better proof, right? You're proving a stronger result. So here's the idea. Okay, and I should say for us, assumptions are going to mean axioms like of set theory. So the idea is we have a theorem we want to prove, and we want to find the weakest set of axioms that can prove that theorem. Okay. Now this is called reverse mathematics. We've been doing this about 50 years, and empirically, there's about 5 systems that show up time and time again. Okay. So in order of increasing strength, they're called RCA. So that corresponds to computable things you can do with a computer. Weak Koenig's lemma, that's at the level of proving compactness. Then you have ACA, which allows you to quantify over natural numbers. You have ATR, which allows you to talk about ordinals. And the strongest one, Pi11CA, allows you to quantify over real numbers. Okay, so those are the 5 systems. Now let's talk a bit about Kurzweil's lemma. So we'll review Riemann integration first, right? So we've got this function, we want to approximate the integral, let's say. So one way we could do this is split up the unit interval, and within each sub-interval, we're going to pick what's called a tag point, right? And then to approximate the integral, we're going to draw rectangles like this, right? And the idea is as the blocks of our partition get smaller, we want these approximations to converge to something, right? The actual integral. Now the problem with the Riemann integral is it doesn't always converge, right? So there are some famous examples which you can't Riemann integrate. So the way we can fix that is with this concept of a gauge. Okay, so the idea is some of our partitions are bad because they give us a wrong answer. So the gauge tells us which partitions we allow. Okay, so a gauge is a positive valued function. And the idea is that the smaller the gauge is, that it means our partition needs to be finer around this point. Okay, so we have this notion of a partition being delta fine for a gauge delta, which, okay, I'll draw you the picture. So a partition is delta fine if all of these balls cover the unit interval, basically. Right, so this one's not delta fine because this part of the interval is not covered, right? Whereas this one is delta fine. All right, so Kurzweil's lemma says that for every gauge, there is actually a delta fine partition. I'll give you the proof quickly. Okay, so we start with the unit interval, and we want to ask, is there a point in here where the gauge is greater than 1? Okay, and if there is such a point, well, we've found a delta fine partition, right? So that means this point is going to cover the whole interval, so we're done. If not, what we're going to do is split up the interval and ask, well, does each half have a point where the gauge is greater than a half? And if yes, we're done on this bit. If not, then we split it up again, right? And we keep going. Now, I claim this has to terminate eventually, because if it doesn't terminate, well, then that means we're going to get sort of a nested series of intervals which have no good points in them. Okay, and these are converging on a single point, right? Somewhere in the intersection. Now, because of the way we've defined these, that means delta at that point has to equal 0, right? But that's a contradiction. We said that the value has to be positive. So it must terminate eventually, and that gives us a partition. Okay, now the question is this the best proof? Well, so when we did that question, we were asking, does there exist a real number in here, right? So we had to quantify over real numbers. That uses Pi11CA, which remember is the strongest system out of those 5. So that's not great, right? We want to prove it in the weakest system possible. Can we do better? Yes, for continuous gauges, we actually only need weak Koenig's lemma, which is the second weakest system. Okay, and I'll quickly talk about, we can extend this to Baire 1 function. So Baire 1 function is a pointwise limit of continuous functions. right? Which doesn't have to be continuous. So here's an example. Now I've looked at Curzon's lemma for Baire 1 functions. We know that's between ACA and pi1 1CA. And again, you can talk about Baire 2 functions, pointwise limits of Baire 1 functions. And we know that's between ATR and pi1 1CA. All right, I'm out of time, so thank you.